We try to prove a result in elementary number theory regarding the GCD and LCM. Of course, the notation here is, for the parentheses here, it means GCD, that is greatest common divisor. And for the bracket here, it means LCM, least common multiplier. Now for two numbers or three numbers, right? So what we're saying here is that the LCM of the three GCD, right, is equal to the GCD of the three LCM. Of course, A, B, C are three integers. Pause the video and try to prove it. In order to prove this fact, we're going to introduce some background. Now, the first, we're going to review that the unique factorization of integers, or sometimes we call it fundamental theorem of arithmetic. So that is, for every positive integer, except for the number 1, that can be represented in exactly one way if we ignore the rearrangement of the order, right? So in other words, the order doesn't matter. So it can be represented exactly a unique way of a product of one or more primes. For example, year 2023 is 7 times 17 squared. Okay, so that's called unique factorization of this integer here, right? Of course, 2024 would be a different value, 2025, right? So that's just a few examples. Now, for the GCD of two integers, right? So earlier we have these two quantities here. So the GCD here happens to be 1 because there's no common factors. There's no common divisor other than number 1. Yeah. So for another number, 1000, in this case, we know that GCD of first two numbers are 1. However, for 1000 and 2024, they do have a common factor of 2 to the third power. That is the greatest common divisor, right? So how is this related to the unique factorization of two integers? All right. That is, for two integers, if the factorization is with these exponents k1, k2, kr, and l1, l2, lr for integer m and n, notice that for this p1 through pr, they are distinct primes. It is possible some of the prime does not appear in the prime factorization of m or n. In that case, we're going to take the exponent to be 0, right? So that is, in p1 and pr is going to be union of the primes that we found in m and n. Okay. In this case, we claim that the GCD is going to be this exponent u1, u2, ur is going to be minimum value of the two. In other words, when you look at these, you pick the smaller value, right, between k1 and l1, and you put as exponents. We can take example here for a and b, and this is 3 and 17, and the 17 here is going to be 0 here. It does not appear. So the GCD is going to take 17 to the 0, which is 1. In other words, it will not be in the GCD. In the GCD here is going to be 3. I'm going to leave this as an exercise. However, in order to prove it, it's good to understand a related fact regarding the exponents here. So what we do here is that if we have product of two integers, you know that the exponents multiplication is going to be just simply addition of the exponents here, right? For the exponentials here, like 3 to the second power times 3 to the 1st power is going to be 3 to the third power, right? And 17 here does not appear in B, so it's going to be 17 to the 0th power, so it's going to be 17 here. So that is the product. From here, what do we know? That the exponents of the product is going to be the summation of the individual numbers. That's an important fact that you can use to prove the previous results, right? So now we introduce a terminology that is for sometimes we call it order of p in the factorization of integer n. Sometimes use another notation, nu p of n. That is, what is the maximum power of p to the k that divides n? All right, this is nothing but the exponent in the prime factorization of integer n. All right, so for example, in this case, if n is 2023 and 7 and 17 square, right? So in the case when n is 2023, when p is 7, the power is what? Is 1. When p is 17, the maximum power is 2. All right, and so we have this notation here is going to be 1 here. This p is 7. For the 17, it's going to be 2. How about some other prime number? It does not appear here, so it's going to be 0, right? So because the maximum power, that could be, if it's not a divisor here, it's going to be 0. Okay, with this notation, we know that if we review the earlier multiplication of integers, exponent is simply the addition of the exponents, right? So what we have is the order here, the new p of a plus b is going to be new p of c, right? That's just simply the rule of exponents. And here, if a is a divisor of c, we know that for any prime p, the order in A is going to be less or equal to the order in C, okay? Because these two results, right? And this new here is going to be non-negative values, right? So, okay, that's the result you can use to prove these results, okay? I'm going to leave this as an exercise. And similarly, for LCM, that is least common multiplier, you're going to have similar results. The only difference here, we're going to take the max value of the exponent here, right? So this is something that you can prove offline. Please do that actually. Try to have a rigorous proof. We're going to use it in our original problem, that is, we try to prove this quantity here, right? We try to prove that the LCM of the 3 GCD value is equal to the GCD of 3 LCM. All right, let's go. We're going to consider P in the prime factorization of A, B, and C. All right. So what is P? Remember earlier we said that there is P1, P2, PR distinct primes. So that set is going to be the union of the prime you're going to find in A and B and C. So for any prime in that set, we're going to consider the order. Right? So for example, new A is going to be I, new B is going to be J, and C is going to be K. Now IJK, it could be 0, right? If the P appears in A but does not appear in C, then in this case K would be 0, right? Now since in our equation A, B, C are symmetrical, so it is okay to assume the I, J, K such that I is the smallest, K is the biggest, J is in the middle, right? They could equal to each other, of course. So with that, we're going to consider in this prime P, what is the value on the left-hand side versus the right-hand side, right? So now when you think about it, for A and B, the GCD is going to take the smaller value, right? So that is the new, for the ABC, the P in that GCD here is going to be I. I is the smallest, right? So what we have is for the GCD of AB, you take the smaller value. See, for BC, you're going to take the smaller value, that is J versus K. Of course, that would be J. And for CA, you're going to take the smaller value, which is I, right? So now for the LCM, because the quantity on the left-hand side is going to be LCM of this 3 value here, AB GCD, BC GCD, and CA GCD. And the new value is going to be max of that. In this case, would be J. Okay, so what you get is the P in the left-hand side quantity here, that is LCM of 3 numbers, is J. Okay, how about right-hand side? Let's do that. So using our early result regarding the LCM, we know that for the AB, you're going to take, the bigger value, right? That would be J, okay, for the LCM. Now for BC, you're going to take the bigger value, that would be K. For CA, you're going to be taking the bigger value of I and versus K, and of course, it's going to be K again. Yeah. And for the right hand side, you're taking the GCD of 3 numbers, so the new value here is going to be smallest of that, so that would be J. Okay, so that's identical to the result for the left hand side, they're both equal to J. So that's for any prime factor, you're going to have the order here is going to be the same. So that means the two quantities are identical. All right, that's a proof. So here we understand the importance of the notation so that the argument is easier to understand with this notation. Let's look at an example here, right, for A, B, C here. Now, earlier from our proof result, we know that the left-hand side, right-hand side would have the power in the middle value, the J, remember? So we know that the left-hand side, right-hand side, for 2, the middle value is going to be, 2 does not appear in B, so it's 2 to the 0th power, the exponent middle value is 1. And for 5 is also 1. For 7 is going to be 2. So in other words, the quantity is going to be 2 times 5 times 7 squared, right? Because 7, the middle value J here is 2, right? So now we're going to verify this, right? What is the GCD of A and B, right? So this is going to be 7 squared. And similarly, BC is 5, and this is 2 times 7, yeah? So what is LCM? LCM is going to be 2 times 7 squared times 5. And for the LCM of 3 pairs, it's going to be here. And what is GCD? You take the common factor that is smallest. It's going to be 2, and it's going to be 5, and that's going to be 7 squared. All right, so that verifies the results. Notice that we have the proof by using this notation here, the new value of P in prime factorization of M, and also we use some results about the GCD versus LCM. All right, so hope you follow the steps. Please like, share, and subscribe to the channel.